Good evening, everyone, or good morning or good afternoon, depending on where you're joining us from. My name is Sam Nasser, and this is the Cleveland C Sharp VB.NET user group. A little bit about the group. Uh, we meet every month. The meetings are free of charge and open to the public, and we cover a variety of topics related to .NET. You can find all the meeting information posted at meetup.com at the link listed below. As always, we'd like to give a big thank you to our sponsors. This week we have a new sponsor, ProTech Training, based out of Pittsburgh. We'd like to thank the .NET Foundation for sponsoring the meetup space. And last but not least, NIS Technologies for sponsoring the go-to meeting space. Before we go any further, I wanted to pause for a second and welcome Scott and Emma from the ProTech Training Group. We'd like to thank you for being sponsors. Scott, what can you tell us about ProTech Training?
Oh, Sam, thank you. Thanks. And thanks everybody for taking a moment here. Project is a information technology training and consulting company based in Pittsburgh. We're actually a global company. We started off as an IBM business partner, working on large systems, mid-range, AS400, System Z mainframes. Got into Microsoft kind of lately, about 2010 or so, 2008, right around the time of the financial crisis. You may remember Riverhead Training in downtown Pittsburgh. Unfortunately, they shuttered their doors and absorbed the company into Project. A lot of the employees came to work for us. And so we became a Microsoft partner. And as a global provider and working with large enterprise accounts, we became what's called a managed partner for Microsoft because we work with a lot of their larger, more important accounts around the country or really around the world. And local clients include companies like KeyBank, Progressive Insurance, Medical Mutual, American Greetings. So it's usually the large Fortune 500 accounts that we typically work with. And our training division is the larger part of our company. We're kind of the flip of most companies where they're a consulting business and training on the side. We're actually mostly training with a very specialized IBM consulting practice. We are on the web at protechtraining.com, as you can see from our logo. And I have here our Cleveland rep who's just recently joined our company. She's a recent OU grad, go Bobcats. And she's just been with the company for a couple of weeks now, so go easy on her. And she is going to be covering the Cleveland region, and she is based in Cleveland. So hopefully, if you ever do have a physical event, she'll hope to get to meet you in person. Thank you.
That would be great. Excellent. Well, great to meet you both, and thank you for joining us. And you were kind enough to offer a sponsorship gift of a $100 Amazon gift card, which we'll be raffling off later using the eval forms. So thank you in advance for that. Continuing on, wanted to also mention that we have a special offer from Manning.com for 35% off a selection of books. You can use the discount code MTPCLEC21, and the link listed below will be available in chat for later browsing. Also, some general information. Please keep in mind that participation is highly encouraged. And like I always say, the only stupid question is the one not being asked. So jump in at any point in time with a question or a comment. However, when not speaking, kindly ask you to mute your microphones just to avoid any background noise. And we always like to keep it casual but organized, meaning you don't necessarily have to wait a spot for the speaker asking for questions, but feel free to jump in at any point in time. However, we want to give our speaker enough time to go through the slides and the demos. And lastly, the presentation is being recorded and will be posted on YouTube in just a couple days afterwards to allow for editing. And the link for that will also be made available in chat. And so for tonight, we have our feature presentation, Turning Software into Computer Chips, by Zoltán Lehóczky. I hope I'm pronouncing that correctly, Zoltán.
That's fine.
And Zoltán is joining us from Budapest. He's the co-founder and managing director of Lombiq Technologies. He's the originator of the Hastlayer project, which he'll talk about in just a little bit. And he's been focused on .NET software development and architecture for the duration of his career. He is active in the open source community, a core contributor of the Orchard project. And he's also a guest lecturer at universities and other user groups. And so with that, we'd like to welcome you, Zoltán. Great to have you with us.
Thank you very much. And it's great to be back because it's actually my second time here. Back in 2017, I already gave a talk. So It's awesome.
Very good memory. Absolutely right. All right, I just
And
made you presenter, so go
yes.
right ahead.
All right. And indeed, Hastlayer, and the tagline here being something more enticingly magical, but we'll get to the roots of it and why it's not that much of a magic, but just, well, .NET. Now, why I wanted to bring this talk to you is because as .NET developers, you probably know or have a rough idea of what you can achieve with .NET code. But perhaps creating computer chips is not something that yet crossed your mind. So let's see how you can do that. By the way, I'm from a company called Lombiq Technologies. We day-to-day do web development actually with the Orchid Core content management system that Sam also mentioned. We are the worldwide market leaders in that technology with clients predominantly from the US actually, including Microsoft itself or Fortune 500 companies like Live Nation or the Smithsonian Institution. But when we are not doing web development, then we are doing some research and development, like our Hastlayer project. But before going into that, let's talk about you. Now, let's suppose that you are working on some kind of number crunching application, algorithm, problem. And by number crunching, I mean something in the areas of AI or machine learning, or the currently quite fashionable large language models. Or you do something with images, be it single still images or videos. Or you work on financial computations, whether that be some back office processing for investment banks or algorithmic trading on the stock market. Or you have something to do with large data streams and you need compression, or you do something in the cryptography or even cryptocurrency space. Now, if you have an application there and it's not fast enough, then you have a couple of ways to make it faster. And this is the usual runbook that you follow in a .NET software. Because, well, first you try to figure out what's slow and try to make it faster. So you use a profiler and you try to optimize your algorithm. Now let's suppose that you have already done that, or the second approach or the second step you can take is that you try to parallelize it. So instead of doing sequential computations, you utilize the multiple processor cores or multiple processors in a server machine and, try to hand out the task to each of them. Now, let's suppose you have already done that. And lastly, you can use, of course, more computers or faster computers. In the cloud, you can quite easily scale up and out. Now, let's suppose that you have already done that, or there's nothing more feasible you can try. So if you have infinite money and infinite time, surely you can do more of these, but it gets unfeasible at one point if you have not infinite resources. And at that point, you can try heterogeneous computing approaches. And that means using something else for computations than the CPU in a given machine. For example, utilizing GPUs, so video cards, or FPGAs. Now, let's talk about FPGAs a little bit more. FPGAs or field programmable gate arrays are pretty much computer chips that can behave like any other computer chip. Although they do have a capacity, so this is with limitations, of course. That means that you can pretty much dynamically rewire an FPGA. So, for example, if you want an FPGA to compute some physics calculations for your video game, you can configure it to do that. Or if you want it to recognize cats on pictures, you can also configure it to do that. Now, even if you haven't worked with FPGAs before, directly, I mean, I'm pretty sure that you have use them in some way, even if you didn't know. For example, if you Google something on Bing, then you have used them because Bing utilizes FPGAs for some compute acceleration. Azure as well, so if you have hosted anything in Azure, the data going in and out of your application was going through FPGAs because Azure uses FPGAs for networking. But FPGAs can be sometimes found in household appliances like routers, or less household appliances like X-ray or MRI machines. And self-driving vehicles also sometimes utilize them among GPUs to accelerate processing. But when it comes to FPGAs, we are talking about hardware development. You have to kind of create a logic chip or a logic circuit, and because of that, the knowledge you have to have is, well, hardware engineering knowledge. Now, to alleviate some confusion, although I just showed you a picture of a chip, and the FPGAs usually have visible circuit boards, like the one I will show you in a minute, they have actually nothing to do with something like a Raspberry Pi that looks similar from a distance, because a Raspberry is just a small computer. Similarly, Arduinos are something else as well. They are microcontroller platforms. Now, why should you care? So what's in for you with FPGAs? Well, the big thing here is that FPGAs have some unique computing benefits. They are good in some things that GPUs and CPUs aren't. So let's take a closer look, but this will be just a totally non-scientific, very crude overview, just to give you an idea. So that's why we don't even have numbers here on the axis. So let's talk about parallelism. So how many things you can compute at the same time? Now, when it comes to CPUs, I would argue that they are on the lower end here, because in a CPU you have like 4, 8, 32, 64 cores, but that's about it. Now, GPUs, on the other hand, are highly parallelized devices. They have thousands of little processing cores. Now, those cores are a lot simpler than the cores in a CPU, but still, you get a much higher degree of parallelism. And FPGAs are kind of in between, because although you don't really have cores in an FPGA, though that's not entirely true for all of them, the level of parallelism you can get there is in the order of hundreds. So, like getting a multiple 100 core processor. Now, the complexity of programs is a different question. So, what can you run on these devices? And CPUs win here because if it's a software, you can run it on a CPU. GPUs, on the other hand, have a much simpler programming model. You can't just run anything on a GPU. Whereas FPGAs are kind of in between again, although you are not running a program on an FPGA. You create the logic in hardware on an FPGA. You kind of create your own processor. But still, the complexity of algorithms, let's say, that you can execute them is somewhere in between. And lastly, power efficiency. So how many things you can compute with 1 watt of power. And FPGAs really shine here because they are highly power efficient devices because they only compute what you need to be computed. CPUs and GPUs are roughly on the same level here. Of course, all of this highly depends on the specifics, but they are general purpose devices. So there's a lot of inefficiency that's not there with FPGAs. But there's a downside to all of this with FPGAs, and that's that it's quite hard to utilize them. Because, programming a CPU or a GPU is easy enough, but you don't program an FPGA. You have to think in terms of wires and logic gates and clock cycles. It's super low level. It's not programming. It's hardware design. It's logic hardware design. But with tools like Hastlayer, we intend to bring this complexity down onto the software development level. So speaking of which, what's Hastlayer actually? Well, it's a tool that takes a computer program and creates some equivalent FPGA logic. Or we could also say, as it is in the tagline, that it takes a computer program and creates an equivalent computer chip. We could also say that Hastlayer tries to get out the logic that you have in your software and tries to create some equivalent logic that computes the same thing in hardware form. And of course, we are at a .NET meetup, so not just any software. We are talking about .NET. And we are indeed talking about .NET in general. So not just C#, but any .NET language, at least in theory. Because what Hastlayer processes are the .NET assemblies. It decompiles the .NET DLLs with the help of the libraries of the .NET decompiler ILSPy. So all in all, what we are shooting for is having the compute benefits for all of us software developers. That means that when you have a highly parallelized and compute or memory bound software, then you can get a very substantial performance increase. Secondly, you can get a much higher power efficiency. And of course, power efficiency here is not just for its own sake. That means costs, lower operating costs, because, you know, when it comes to computing, you pay twice for power. First, you pay in the actual power that you use, and secondly, you also need to cool that heat away, which is kind of a limiting factor in a lot of data centers. And it's still software development as usual. So a lot of talk until now. Let me now show you the whole thing in action. So I will now switch over to Visual Studio and show you how you can utilize Hastlayer. What I'm showing you here is a class called Parallel Algorithm. And you might not have guessed, but this is actually a highly parallelized algorithm. This is, by the way, not a real-life example. This is kind of an exaggerated example of the kinds of algorithms that are especially suited to be accelerated by FPGAs with Hastlayer. And what it does, the core of the logic is down here. By the way, the whole thing and everything else that I will talk about today and the whole of Hastlayer is up on GitHub. It's fully open source. I will also show you the link later, so you can check out all of this in more detail on your own too. Now, here's the logic. It's, again, not something useful. We are kind of simulating some kind of number crunching, some kind of compute-bound algorithm here, because there's some conditional logic here, which is executed 10 million times. And the interesting thing here is that we are doing this in tasks. We start a new task for this. Now, I suppose most of the people here are familiar with tasks and the task parallel library of .NET, but if not, you can think of them as an abstraction over threads. So basically, what happens here is that we are starting potentially multiple threads and compute this logic all in parallel. And actually, we start this many threads, or this many tasks rather, which is 260. Now, what's this magic number here? When we start these 260 tasks in .NET, then how many actual threads will be used and what the hardware level parallelism will get depends on the CPU and the utilization of that CPU. So .NET in the end will decide how many threads will run in parallel to maximize throughput, but not to oversaturate the CPU, regardless of how many tasks we start. But when Hastlayer takes this piece of code, or rather the assembly that contains the compiled version of this code, and creates the equivalent hardware logic, it will create something like a 260 core processor that can't compute anything else, just this class, just what we have here. And 260 because that many will fit on that particular device I have here. We'll also check that out in a little bit, in more detail in a little bit. The rest of the code here is just some plumbing and waiting for the task to finish, also returning some output, and pretty much that's it. We also have more useful algorithms in among our samples, so again, you can check them out if you are interested. But let me actually start this whole thing and run this code. And what I will use for this demo is this device here that I'm showing to the camera now. This is actually something like an onboard computer on a satellite, because Hastlayer works in the cloud, including Azure. It also works on premises with smaller and bigger FPGAs. But this is probably the most curious among these, because really this is the same thing that goes on board of a satellite. And I figured that probably it would be more interesting to show you that you as a .NET developer can also write apps for satellites with hardware acceleration. So since this is kind of an onboard computer, it's not just an FPGA, but it also has a CPU, and it's a little computer that runs Linux. So I'm now opening a terminal to it, and I'm remoting into that Linux, and I'm starting a little demo application here. What happens is that on this onboard computer, Hastlayer starts, and it generates a hardware implementation for our code, and then it starts to execute that parallel algorithm example as software. So this device here has a 2-core small ARM CPU, so pretty much what you also have in your phone, but most possibly a lower power version. And it also has an FPGA, an FPGA that's roughly equivalent in its sophistication and in its costs. So it's not apples to apples, but of a comparison, but still it's a fair comparison, I would say. And it finished, so let's see the result. And here's how long it took on the CPU. It took roughly 25 seconds. So it was something that took quite a bit of time. Now let's check out the hardware execution. And we actually have 3 of those. The results of the first one are here. It took around 240 milliseconds when we take just what happened on the FPGA itself, and it took about 330 milliseconds when you also take the communication round trip between the ARM CPU and the FPGA into account. The FPGA here is actually on the same chip, but they are connected via PCI Express. So that's already quite good, but let's take a look at the second execution here, which is here. And in that case, it took exactly the same amount of time on the hardware, but altogether it took much less, around 250 milliseconds. This was a lot faster than the first execution because we are talking about .NET, so there was some JIT compilation going on, some caches weren't warm. So now the second execution is what's actually representative. And as you can see, it's about 100 times faster. We had 25 seconds for the CPU execution, and we have 250 milliseconds for the hardware execution. Now, of course, again, this is not a real-life example, and your mileage may vary with actual real-life examples, but still this shows you that you can get 100 times speed increase just by utilizing Hastlayer. And speaking of utilizing it, how do you actually integrate a Hastlayer compatible algorithm into the rest of your app? Because this parallel algorithm that I've shown you was just a single class, and you need something to get to that FPGA, to utilize Hastlayer, to tell it what to do. And we have an example of that here too. So if you have an existing application, this is how you would execute a Hastlayer accelerated software from it. Now, this is, by the way, a small console application, but this is just for the demo. You can substitute it with any kind of application. And first, you have to do some configuration, which is basically here telling Hastlayer that which device you are using and what's the class that you want to be able to reach from the host PC or from the CPU, which in this case is, well, parallel algorithm. Secondly, here's the actual hardware generation part. This generate hardware async method call is where most of the magic happens. This is where Hastlayer generates the hardware code. And here, by the way, we tell it to process the assembly, the parent assembly of this parallel algorithm class. And finally comes the execution itself. And the main thing is here. Well, actually, rather here. So how you run something, how you run the run method on that class is actually like this. And you can see that the curious thing here is that there's nothing really special. It's just .run, and that's it. Well, there's one thing required here still, and that's this generate proxy async method call. Here what happens is that we take an instance of that parallel algorithm and we let Hastlayer wrap it into a dynamic proxy. What this allows Hastlayer is to hijack method calls that go to that class. So when we call run, seemingly on that class, or rather on that instance of that class, then really what happens is that Hastlayer takes over and transfers the processing to the FPGA. Again, this code is also up on GitHub with many more examples if you like to see the whole thing in detail. So now I've shown you how Hastlayer can be used and how you work with Hastlayer, but I haven't yet told you how it actually does its magic. So let me show you that. This is the device I've used for the demo. What I'm showing the picture of here is just a smaller part of the whole board that I've shown you. This is what goes on an actual satellite, and it's a little smaller than a credit card. So the picture is actually on your screen a lot bigger than the device itself. And the FPGA is that chip in the middle. Actually, it's not just an FPGA, but as I mentioned, it's an ARM CPU plus an FPGA on the same chip. And this little board goes into a bigger board that I've also shown you. It's a development board that we use to actually be able to work with the device when it's not on board of a satellite, and it has, for example, Ethernet ports and USB ports. And now let me show you how that generated hardware actually looks like, because what Hastlayer creates is some code, but it's not software code, it's hardware code. And here it is. What I'm showing you is an example of a file that Hastlayer spits out. It looks like some kind of code, and we can even see something like function and if else. These look like part of a program, but this is not a program. This is code, but this is hardware code. This is actually written in the language called VHDL, and all of what you see here eventually will be converted into actual wires and logic gates. And if we scroll down a little bit, we will see something familiar, the parallel algorithm name here. And actually this whole block here relates to our parallel algorithm. It's not the whole logic that's in that class. Rather, these are just type declarations, like in .NET variable declarations or adding a property. But why I'm showing you this is because if you check it out closely, this piece has the index 0. And if you scroll down a little bit, we see exactly the same thing, but with the index 1. And then the same thing again, but with the index 2. Now, can you guess where I'm getting with this? Because if we scroll down a little bit even more, we get to the same thing with the index 244, and some more, we are now at the same thing again with the index 259. Now remember that in Visual Studio, in this parallel algorithm sample, I told you that we are starting 260 tasks. Well, those 260 tasks on the hardware are manifested in these 260 copies. So really what happens here is that with this FPGA, we caught a 260 core processor just for this class. It can't compute anything else, but what it needs to compute for us, it does it in a very efficient and very fast manner. Because this parallelization, this actual hardware level high degree of parallelization is what provides the performance benefits, and that it's hardwired and that the FPGA just computes this provides the efficiency, the power efficiency benefits. Now, what else is there? We actually support a technology or a platform called Xilinx Vitis. The device I've shown you here is manufactured by the FPGA company Xilinx. And their Vitis platform is a little bit like .NET for FPGAs. It allows you to target Vitis, and by that you get support for a lot of FPGAs. This is actually a very big thing because unlike when it comes to software development, there's no interoperability or cross-platform nature of hardware code. Your hardware code has to be specific to a given device. This is still the case here, but it's a bit easier. And because of this, with Hastlayer, we can support pretty much all the high-performance FPGA cards that are already available in cloud providers and also in on-premises, in custom data centers. This includes Azure as well, as I mentioned, AWS, Alibaba Cloud, some smaller cloud providers as well. And this also means that the aerospace industry use cases are also readily available. This is why I could show you that you can write hardware-accelerated code for a satellite's onboard computer. We are actually working on putting it into a real satellite up in orbit. We also did some benchmarks. The details of these are again up on GitHub. And on the data center accelerator cards, so the big expensive cards that are available also in Azure, we got these numbers, pretty much a speed up starting from 4 times faster all the way up to more than 30 times faster, and the power consumption advantage was 20 to 120 times. Now, when it comes to the onboard computer, so what I've also shown for the demo, then the numbers are a little bit different. They are actually a lot better. Now, keep in mind that this doesn't mean that the small onboard computer is faster than the large data center accelerator cards. With these numbers, we always try to be as fair as possible, and we are actually comparing the FPGA with a CPU in the same device. So in the case of Xinx, we compare to the ARM CPU, on board. And in the case of the FPGA boards in Azure, we compare to that huge CPU that's in that machine, that server machine. Some other curious thing is that you can also create your own number format in a hardware accelerated form, actually. Now, creating your own number format is possibly not something that you do every day, but that's actually something that's quite prevalent in the machine learning space, because there pretty much every bit matters, both for storage and computational speed, but you don't need that level of accuracy. So something like a neural network is usually happy with just 8-bit numbers even. And what we have done is that we have taken a new and innovative number format called POSIT. That's not developed by us. It was created by a mathematician called Dr. John Gustafson, who works on this in Singapore. And what we have done is that we have created an implementation of this in .NET. We pretty much created a struct that's such a POSIT number. And with Hastlayer, with the push of a button, pretty much, we created a hardware implementation of it as well. Now, such POSITs promise to be a lot better than those standard floating point numbers that we all usually use, so the double and float types in .NET. We will see how it catches up. We want to have a lot more use cases for Hastlayer, so if you have something that would warrant such hardware acceleration, please let me know, and I would be more than happy to help you get going and see whether Hastlayer is a suitable software for you or a suitable tool for you. We also engaged into a partnership with the Wigner Research Center for Physics, which is an institute that specializes on physics research. I know, shocking. And with them, we evaluate whether Hastlayer is suitable for scientific computations, because scientific computations and something like engineering simulations are also the areas where such hardware acceleration makes a lot of sense. And it seems that FPGAs are now quite readily available. As mentioned, all major cloud providers have them. And the CPU manufacturers also woke up, because Intel actually acquired the then second largest FPGA manufacturer called Altera. And AMD also relatively recently acquired the largest FPGA manufacturer called Xilinx. So CPU manufacturers also know that Moore's law can't go on forever, because we are now reaching physical limits. You can't just put more transistors on a chip, and because making the transistor smaller just won't be possible forever. But you can optimize the architecture. You can optimize what you do with these available transistors. And with FPGAs, you can basically add a core to a CPU that's application specific. And it can be application specific for every application, because you can swap out what that FPGA does. It's reconfigurable. So to wrap it up, if you like this, and I really hope you did, then go check it out on GitHub. I have the link here, but I will also add it in a comment under the meetup event. So don't worry. And be ready, because I think FPGAs are coming. I would say that with FPGAs we are roughly on the same level where we were with GPUs maybe 10 years ago, because GPUs started as something that specialists use. Specialists use in special use cases for video games, for graphics computations. And then some people started to hack around and start to utilize them for scientific computing and other kind of computing. And eventually this became a standard thing, not just a hack. GPU manufacturers also started to support this explicitly. People got proper development environments and everything. a similar shift is happening with FPGAs, because a couple of years ago, FPGAs were also only for specialists and not really for hardware acceleration, rather for hardware design work. Because when it comes to something like designing a CPU, FPGAs are actually used for testing, emulation. But, well, we don't care about that. We just want to make our software faster with them. So, thank you for your attention. If you'd like to get in touch with me, here are my contacts. And now probably we have a little bit of a discussion, some Q&A, if there are any questions.
I certainly have a few questions, but I wanted to open up the floor to any of the other folks joining us. If you have any questions, feel free to jump in. And if not, maybe I can bombard you with a few questions.
Yes, please.
So obviously this is code that's going to be on a chip. So let's say right now I'm developing an app and it's on .NET 7, but in another 2 months or so, when .NET 8 is released, I need to upgrade to that. Do I need to replace the FPGA completely, or am I just reprogramming it again?
You are definitely just reprogramming.
Okay.
Perhaps that wouldn't be necessary either, because so what happens, as I mentioned in the beginning, is that Hastlayer tries to get the logic out of that .NET assembly. Now, if the logic is the same, even if the .NET version changes, then that means that Hastlayer will produce the same code. You don't even have to update the FPGA. You don't even have to reconfigure the FPGA, to be more specific. But definitely you don't have to throw away that FPGA. You can reconfigure it pretty much indefinitely, well, as long as its flash memory works, because it also needs a flash memory to store that configuration. And yeah, you can do that all the time.
Okay, very good. Now, let's say that I'm developing an application that accesses a database. Where would I specify my connection string? Can it be dynamic, or would it have to be hard-coded?
Now, to clarify something before answering your question, not everything that's available in .NET is actually supported by Hastlayer. So there are limitations, and most of the limitations are around what makes sense. Running a piece of logic as hardware is very different than running it as software on a CPU. And because of that, for example, writing to the console doesn't make sense on an FPGA, so we don't support that. There are a couple such things as well. When it comes to database access or accessing I/O in general, then that should happen on the host PC. What we are talking about with Hastlayer and with FPGAs is that you take a piece of the computation, the computationally intensive part of your algorithm, and offload that. It's pretty much like how you offload graphics computations to a GPU even, or how nowadays sometimes machine learning computations are offloaded to a machine learning accelerator. You don't access the database directly there, rather that happens in the host app, and you pass the data, the inputs to the FPGA pretty much.
Okay, fair enough. So let's say that I come up with a computation for calculating the square root of a number. And I put that, I run it through Hastlayer and I burn that on an FPGA. Now, when I write my code that's going to be accessing that computation, in my code, am I accessing a NuGet package? Am I accessing a library call to be able to call that code that's on the chip? How would I do that in my .NET code?
You pretty much need to pull in a NuGet package. By the way, this part is also documented under GitHub. I'm not trying to deflect the question, just for your information if you would like to check this out in detail.
Right.
But how it happens is that, yes, you add a NuGet package, and then you pretty much do what I've shown you in this part. So this, what I'm using here, by the way, is the Hastlayer SDK code. So something that you can look at, but you don't need to use. This is what we work with when we work on Hastlayer itself, and when we create the examples, for example. The examples are here. This one is part of the demo app. And this is pretty much what you would do. Some configuration in the beginning, hardware generation, and then you would just call the methods that contains the square root in this case, although that probably doesn't make sense to accelerate, of course. Mm-hmm. You would use like the square root methods here, or call the square root methods here, and the rest will be provided by Hastlayer.
Okay. I have one more question, but wanted to pause and see if anyone else has any questions so that I'm not taking up all the time. Okay, so if no one's jumping in, one last question, Zoltán. So you had mentioned that I would need an electrical engineer to get this installed on my server box. What exactly is going to be happening? Is this going to be inserted as a card on my motherboard, or do I need to have a customized motherboard altogether? What are the essentials that are needed there?
Okay, some clarification there. I said that you need to be a hardware engineer to utilize FPGAs in the traditional way, but not anymore. So you as a software engineer can very well utilize FPGAs with Hastlayer. That's kind of the innovation here. And otherwise, yes, an FPGA is a card, an accelerator card. So what I've shown on one of the slides here, this guy in the lower right corner, that's a card that goes into a PCI Express slot. As you can see, pretty much how you would do with a video card.
I see.
That's for on-premises, but you don't need to do that. You can also go to Azure and rent an FPGA containing virtual machine by the hour.
I see. Okay. So in addition, expanding on that, if I was running a server farm, would I need a card on each server then?
Well, it depends what you utilize it for. If you want to process something very heavy and you actually need all that computing power, then yes, you would need, or you would likely add FPGA cards to multiple servers at least. By the way, a single server can host a lot of these cards, pretty much as many PCI Express slots you have. That's because when when you utilize Hastlayer, you are indeed offloading all the computations. So on the host PC, you only need enough resources to run that piece of .NET app that communicates with the FPGA, which is very minimal. So you can have like a dozen FPGAs with a very standard CPU, and that wouldn't hurt any performance. You just have to be able to feed those FPGAs both physically and both power-wise.
Okay, very good. I thank you for taking the time to answer my questions. Anyone else have any questions or comments?
With pleasure.
I just had a quick one.
Please.
What's the smallest, I guess, least powerful kind of hardware this can run on? Like, will it run on things like a Raspberry Pi or those kind of electronics?
Mm-hmm. There are specific FPGA boards that we support. As I mentioned, due to the peculiarities of hardware development, we have to support each device individually. Actually, not just the FPGA chip, but also the FPGA board and their combination. So it's madness, but that's low-level hardware design for you. And because of that, we support altogether something like 6-8 cards. 2 of them are relatively small and cheap. One of them is something like a $250 card What I've shown you here is something like $500-600 or something like that. But then again, you can run this by the hour in Azure, which is something like $1 per hour. A Raspberry is something very different, so you can't use that. A Raspberry doesn't have an FPGA chip.
Does that answer your question, Dave?
Yep, that'll do it. Thanks.
All right, very good. Anyone else, questions or comments? All right, I guess that's about it for the questions. Zoltán, thanks again. Great having you. And thanks for a great presentation. Very informative and very interesting topic, something we don't come across a whole lot.
Thank you very much.
So thank you for being here. If you don't mind, I'm going to take back the screen just to have some wrap-up announcements. And
Sure.
Let me go ahead and share. All right, so in the chat window, I posted several links, and we'll cover those in just a little bit. But essentially, you have the link to the YouTube channel where the meeting, where the presentation is going to be posted. Just allow for a couple days for the presentation to be edited and posted there. But if you would please subscribe to the channel to get upload notifications. Also, you can find tech events posted on my blog with the link samnasser.blogspot.com. And then you can also subscribe to that to get notifications of updates. And last but not least, if you joined us shortly after the start of the meeting, we had a new sponsor, ProTech Training, based out of Pittsburgh, and they are offering a $100 Amazon gift card, and that will be raffled off using the feedback eval forms. So if you would please use the link at the bottom of the chat window for the eval forms, fill those out, and then a winner will be drawn at random, and you'll be notified by email. As for another offer that we have from Manning.com, 35% off a selection of books available at Manning.com with the link listed at the bottom of the slide, and that link is also posted in the chat window as well. As always, we always like to ask about job openings. TechSystems always has jobs available at techsystems.com/IT-jobs, but we always like to ask who's hiring and who's looking for work. So if your place of employment is looking to add additional staff, or if you're looking to jump ship and transition elsewhere, please make yourself known either in chat or verbally. And it seems like everyone is happily employed at this time, so no transitions there. All right, and then last but not least, my contact information. You can find me at snasser@nistechnologies.com, or you can find me on Twitter at samnasser. The link to my blog once again. And lastly, if we're not connected on LinkedIn, I invite you to do so. And so with that, if there's no additional questions or comments, Zoltán, thank you again for joining us, and thank you all for joining us for this meeting, and look forward to seeing you all next month. Good night, everyone.